Hello, this is T Chapman 500, and today I'm happy to announce that I finished the demo CPU. So we're going to put the demo CPU here, and then we're going to add some input and output. So we'll have this, and this, and this. Make sure they're all facing the right way. So bring this over to here. This over to here. Hope that's correct. Yep. Then this I'll bring over to here. Move that up so that the wires aren't crossing. Move these down. Then move those like that. I suppose I can bring the address down like this. Bring this down. This down. Bring this up, then, over like that. Bring that down. Actually, I don't think I need it to be that far down, or that far over. So, bring this reset line down, and this clock line down. Now, I have this thing called an address mapper, so it will map the various components that I decide to put in here to the processor. Let me show you how these components work. So we have three 16-bit inputs. So the map determines the base address for each component. The mask defines the range which is checked for that particular address. So, yes. So if I were to make the mask ones on all of the upper bits, and then do 1, 0, 1, 0 for the map, then this would check to make sure that the upper half of the address input was 1, 0, 1, 0. And then the lower half wouldn't matter. It ANDs the mask with the address, and then compares that with the map, which, by the way, the map should be all zeros where the mask is all zeros. Then if there's a match, one of these outputs will be set depending on which of these inputs are set. Okay, so I've loaded a program into the ROM, but before we run it, I want to show you what is inside this processor. So the first thing that we have is this SR latch. This SR latch will reset the processor when the reset line goes high. And the reset line will stay high until the clock input is low. Once the clock input is low, if the clear input is also low, then the SR latch goes low. So this big thing in the center is the control unit. And to the right, we have a number of registers. So the first one is the ISS, or the Interrupt Service System, followed by the Temp Register, followed by the Program Counter, then the Address Register, then the General Purpose Register file, then the Arithmetic Logic Unit, then the Flags Register, then the Instruction Register. So let's go into the Interrupt Service System. And as you can see, we have up here a 16-bit register that's split into two 8-bit registers. That's so we can have a write enable for the low and high bytes. So from there, we have two more registers. One is a D flip-flop that updates every clock cycle. So on the rising edge of every clock, whatever is on this input gets put into this register. And then, if the enabled register is 1, then it gets forwarded to the control unit. Next up, we have the temp register. Now, the temp register can be loaded from the data bus or from the address register. The decrement signal is not used, and I should probably remove it. And once again, we have two 8-bit registers combined, and that's so that we can independently write to either the lower half or the upper half, or if we're loading from the address register, write to both at the same time. The temp register output goes directly to the address bus, almost directly, and can be picked up by either the program counter or the address register. And the address register is also capable of copying its data to the temp register. So next we have the program counter. Here we go again with this 2-register setup. We can load it from the data bus, or the interrupt service system, or the temp register. And this is the first of the registers that also has a data out. So we can send whatever's in the program counter to the data bus so that we can push the program counter onto the stack. We can also send it to the address bus because it would be pretty useless if we couldn't do that. Next up is the address register. Basically the same as the others. We can load it from the temp register, from the data bus. We can store it to the data bus and send it out to the address bus. Notice that for the interrupt service system, it looks like we might be able to send it out to the data bus, but it doesn't go to the data bus. It goes to the program counter. The address register is the only 16-bit register that can be copied to the temp register. And by the way, the temp register only contains valid data for the instruction that loads it. Once that instruction finishes executing, whatever's in the temp register is invalid. Next we have the general purpose register file, which as you can see here has 8 registers labeled R0 to R7. R5 is now the accumulator. If you've seen my previous videos, you would know that the accumulator was a separate register, as was the output register. These have all been combined into the register file so that I don't have to have nearly as many instructions or hardware to allow it to put the accumulator and output register onto the data bus. So if we take a look inside here, we have the select line, we have the data in, data out, we have the ALU in, which actually goes out to the ALU that's on register 5, which is the accumulator. And we are capable of writing to register 5 directly, bypassing register selection. The ALU is also capable of writing to register 6 directly, again bypassing data selection and also bypassing the data bus because it writes to R6 through this thing. It also bypasses register selection by the fact that we can send it directly to the data bus. Register 7 is the stack pointer. The upper half of this stack pointer is hard-coded to be 08 in hexadecimal, and the lower half is from register 7. Next we have the arithmetic logic unit. We have the A and B inputs, which are 0 when the enable wire is 0. We also have the operation input, and this thing right here is just so we can do different variations of addition. Now on a processor, addition, subtraction, and negation are all forms of addition. Subtraction XORs the subtract signal with the B input, and for negation, we simply put 0 on the A input and we negate the actual A input. And to increment or decrement, we simply make sure that the B input is set to 0, and then we force this thing to be high, and we force this thing to be high. So as you can see here, the A input can be sent directly to the output. That will happen whenever we receive a test instruction. I also got rid of the NAND and NOR operations, so that frees up these 2 slots for instructions that don't have to do with the arithmetic logic unit. Next up we have the flags register. Quite simple. We get input from the arithmetic logic unit and we send input to the arithmetic logic unit. We can also load this register from the data bus and send it out to the data bus. The next register is the instruction register. It's pretty simple. Next we have the data control system. This we cannot put in a subcircuit, and this is to make sure that we can put things on to the internal data bus without also putting things onto the external data bus. So This is a way to separate stuff inside the CPU from stuff outside the CPU. And this circuit just controls which of the address registers gets put onto the address bus. Let's go into the control unit. So first thing we're going to note is that the reset signal is connected to the stepper via an OR gate. One input comes from the reset button that we added earlier in the video, and the other comes from a reset signal that comes from these 4 ROMs. Let's take a look at the stepper. It's basically a 3-bit register, so the output to the stepper goes not only to these ROMs, but also to this comparator, which generates a clock signal to this D flip-flop, which is a rising edge triggered D flip-flop. So when the interrupt signal is a 1 and the stepper reverts back to 0, that's when this line will be activated, deactivating these 3 ROMs and activating this ROM. Each of these ROMs has 2 32-bit words, of which only the first 7 bits of the second word are used. So this ROM is responsible for going into an interrupt service routine, and then this ROM would execute a return from interrupt instruction. Each instruction has a maximum of 8 clock cycles to execute, and the first clock cycle is always for loading the instruction. So these instructions will take a minimum of 2 clock cycles to execute. The second clock cycle resets the stepper. Now the reason I have 4 of these ROMs here is for optimization, mainly because of this jump instruction, but also because there's somewhere between 16 and 24 instructions, I believe the exact number is 18, that don't use any embedded operands and take up what would be the operand field of the instruction. So that's what this ROM is for. If we take a look at the contents, we can see that the first 18 entries are fully utilized. And then the rest of what could otherwise be utilized is put here. Then the remaining 8 are left blank. That's because they're not going to be used. These 8 that are blank are used by this ROM. So if we edit the contents here, this is where the optimization comes in. Each jump instruction has 4 rows on this ROM. So this is the unconditional jump that's highlighted, and the rest of these are conditional jumps. And this one is not used. So now we go on to the final ROM. As you can see, the first 4 entries are not used. Those are used by the other 2 ROMs. And the rest of the entries are used except for this entry right here, which is just to make sure that we can execute an instruction. Alright, there we go. Let's reset this again. And there we go. The program is running. It's Fibonacci. And by the way, interrupt. This is the 128 subscriber special, and I actually had to add this in using a hex editor. Anyways, hope you enjoyed the video. Don't forget to rate, comment, subscribe, and share, and also hit the notification icon to be notified of every video I upload. And I will see you in the next video. This is T Chapman 500 signing off.